Hello, Shajid.
Hi, Imran. How's it going?
I'm good. How are you?
Yeah, good, good. I just I got back from Waterloo on Friday, and
Right.
my luggage was missing, and my iPad was in the luggage, so I was extremely worried. How are we gonna do the
Oh,
lectures?
yeah, these
Mm.
things I think have started happening like more frequently. I've heard from other people also that, I recently met someone who was coming from Iran and it
Uh-huh.
was a good airline, but they, missed their luggage somehow. Which airline were you traveling?
I was traveling. It was KLM,
Okay.
the Dutch airline.
Like
But
it was it was their mistake or
no, no, yeah, yeah, it was their mistake. So but I finally I got it back on Sunday. So I actually couldn't wait, so I went down there again and collected it. But anyway, fortunately I have my iPad now because I was
right,
worried that how
right.
I'm do this. Um,
So yeah,
yeah,
we'll
and
just wait a little and we'll begin on time
yeah,
because of course you are already here. So
yeah, I was actually I just realized that I should never uh, plan a talk right after the travel. It
no,
was
I do realize that of course you had a busier schedule than maybe Tibra, and
uh,
so
yeah,
that's
because
kind of you
this
that
week
you took
our
time and
yeah, this week is basically our what is it called? Our semester is actually is starting from this week, and I was I was gone until like Friday, so I moved to a new place, and it's a yeah, I should not. It's a bit hectic, uh, and
of course, no,
so
I totally realize it and. Actually, I think the semester timings are also very variable. Like in Pakistan, the fall semester begins usually in September,
mhm, yeah.
either early September or end of September.
Yeah, I think because in South Africa, in Cape Town, it's when there's summer, rest of the world, it's winter here, right? So right now we have winter. So it's basically it was a short break, and my family lives in Canada, so I just was gone for 6 weeks. Um, but it's a short break because it's a winter break. But in December we get our summer, and then we get a longer break.
Okay,
Yeah.
okay. And like, no, I'm saying this because even Tibra was telling me that even in like, I hope he's teaching in Bangladesh. So there also, like, he's having like this end of semester, like he has exams, end of semester exams going on there. So I am realizing that now this is the spring semester ending there.
I have no idea. I think this is
Okay.
probably either like a squeezed in between semester, or maybe
Yeah, maybe
it's
it
a
could be
longer,
you're right. You're right. It would be the summer semester. Yeah, yeah, yeah.
yeah,
Okay. Because I
like a
think
short, no, some,
their schedule would be similar to ours, but it would
mm.
be the summer semester, and yeah, the fall will be starting from uh, September, I guess, end August or September.
I think so, yeah, something like that. I taught in BRAC actually for a semester in 2013. I was in sabbatical, and then yeah, so I spent some time in Dhaka and was teaching in BRAC.
So you're like originally from which part of Bangladesh?
Yeah, so I'm originally from Dhaka. So
Dhaka.
basically, I grew up in Dhaka. I studied the same university as Tibra. So I did my undergrad, but I'm actually uh, after a few years later, Tibra. But yeah, so we graduated from the same university. But after finishing my undergrad, I did my PhD from Wisconsin.
Right, right, right. Okay, so here we have Tibra. Hello, Tibra.
Hi everyone. I'm not turning on my video if that's all right. I have
No,
Yeah.
it's
my room is
absolutely
a
okay,
mess.
and the vase is beautiful.
Oh yeah, that somebody's painted it long ago.
So,
I
but
like your background too. Yeah.
yeah, thank you. Because I just like I'm not into these things. I just used to usually simply blur the background as Shajeed has done, but I'm trying to be, more techno and get
Right, right.
up with the, so it's nice to hear you after somewhat long time.
Yes.
So maybe we can begin because many participants prefer to, watch the recording of the lectures. So should
Okay.
you can try sharing your screen if that's what you are planning?
Yeah, I
Yeah.
I will probably leave a bit early because I am preparing tomorrow's lecture,
Okay, okay.
if that's okay. And I will get the update from Sajid. Also, while I'm here, I'm gonna mute because I have two dogs in my room and they get excited. They're very excitable, so they might start shouting at some point. So, all right. Well, Sajid, please take it away.
Thank you. Can you see my iPad?
Yeah, it shows that you have started screen sharing. Maybe either my connection is slow or
Oh, okay. I think it's my end. Sorry, forgot my password.
yeah, it's stuck at that you have started screen sharing.
Okay,
Okay,
I
now
think it's
you
working.
can
Yeah.
see.
Let me adjust it a bit. Good. Can you see the full screen now?
Yes, we can see the full screen. So, uh,
Yeah. So should I go ahead or should I start?
yes, let me just, formally begin that we are starting our workshop on string theory, and it's going to basic introduction. And so I would now request Dr. Shajit to briefly introduce himself.
Thank you. Thank you, Imran. My name is Shadid Haq. I am a theoretical physicist. I work at the University of Cape Town in the math department. I so basically my background is I was a string theorist originally, but as most other string theorists, my interest has shifted towards other things. For example, in recent years, I've been focusing more on quantum information theory and application of quantum information theory in high energy physics, in cosmology, in quantum memory systems, and so on. So I have also worked on a little bit of on holographic entanglement entropy, and that's actually the reason why I shifted towards holographic complexity and quantum information theory, because that's sort of the original direction. So yeah, I think that's briefly what my interest is. So I'm gonna start now,
Yes,
if
please.
that's okay. Okay, cool. So so let me give you a start with an outline of this lecture. I'm going to give two lectures. So of course I cannot do a lot, but I'm hoping that some of this, I'll at least give the foundation for Tibra to work on his lectures. So what is let me write down the outline of this talk. So So this is lecture 1. Sorry. This is lecture 1. Now, a brief outline. So I'm going to talk about first the resources that I'm going to use. I'll also try to give a brief history of string theory very fast, and then spend a little bit of time on why we do string theory. And then I'll start talking about units a little bit, and then I'll directly move to relativistic strings. Now, in this context, for relativistic strings, I'll basically start with the relativistic point particle. And then I'll talk about the Nambu-Goto action, and then introduce Polyakov action. So basically, we will go over equation of motion and constraints, and finally solutions and model expansions. So this is going to be the content for lecture 1. In the second lecture tomorrow, I'll try to quantize the strings. Now, for the textbook, I'm assuming some basic understanding of GR and differential geometry and some quantum mechanics that I'll be using to lay out these concepts. Now, the first the textbooks. So I'll for the textbooks, I will heavily follow. I'll heavily follow this very interesting and useful lecture notes by David Tong. I will also use a little bit of Becker Schwarz, this the string theory book. I think it's called String Theory and M Theory. I'll also use a little bit of Zubak. It's I think called a first person string theory. So these are roughly some of the content, some of the resources. Now, so as David Tong mentioned in his lecture notes, I'm going to start with that. So string theory is basically some sort of it's an ambitious project. That's what he called it. So the idea is the main idea of string theory is to develop like a all-encompassing theory of the universe that will unify all the forces of nature, including gravity, in a single framework. So that's roughly what's the goal. Now, the premise is for string theory is the fundamental building blocks of our nature are not point-like particles. Right? So that was the whole essence of the particle theory. Rather, the fundamental building blocks of our nature are the tiny loop-like objects, strings, we call it strings. Now, from this, we can actually derive, ideally, we can actually, the GR, electrodynamics, gauge theories all emerges very, very, very nicely. So it sounds pretty cool, but there is a trade-off, of course, right? It's not, Nothing comes for free, right? So there's a trade-off, and the price we pay is we get a lot of extra stuff when you make this transition from particles to strings. We get a lot of extra stuff. We get a lot of junk, and the idea is how to get rid of the junk. Now, in these 2 lectures that I'm going to give, I'll not have the time to. I'll not get the time to get to that, but I'll try to actually work on the basic foundation, the formula. We'll see some of this when in Tibra's talk. Now, let me start with the like a brief history of string theory. So the idea originated from the study of what you call the strong nuclear force. Right? This is the force that binds the quarks together. Now, so this strong nuclear force. So I'm sorry. Let me keep track of things. So I'm talking about the history now. So the idea is that there is a strange behavior for the strong nuclear force. The force gets stronger with distance, in contrast to gravitational or electromagnetic force. So the question is, what type of force becomes stronger with distance? Now notice that it actually happens with the rubber band. Right? So if I think of it a rubber band, and if I stretch it, the more you stretch, the stronger the rubber pulls back. Now, for the strong force, it actually comes from the flux tubes of gluons. Now, however, this was discovered much later. So this was discovered, I think, in the mid-70s and probably early 80s or something, more experimentally proven. But I'm talking about the 60s, or maybe late 60s. This was not known at that time. So what happened was Gabriel Veneziano was trying to find a way to describe the Slack data. And what he came up with was some sort of function, some sort of, so he basically guessed the form of the function that can fit the data. And it was and he found that the Euler beta function could describe the scattering amplitude of the strong interacting particles. Now, but then when people look at closely, people like Nambu, Nielsen, Susskind, almost in a year or so, they look at closely and they realize that it actually describes an interaction mediated by closed string-like objects, which could be interpreted as a spin-to-particle, which is we call the graviton, the quanta of gravity. Now, so in principle, so it's actually describing quantum gravity. Now, this is remarkable because previous attempts to quantize gravity didn't work, and as they are all non-renormalizable, right? There are lots of infinities that cannot be regularized. Now, so this was basically the original energy behind the string theory, that it's a quantum theory of gravity. But there's some claim that it's probably the theory of quantum gravity, the only theory of quantum gravity. And there are some recent papers on that. Like there was a paper came out in 2024 by Clifford Chiang et al., and they have some assumptions and accepting assumptions. They can argue like that. But I'm not going into that. So that's where my history lessons stops. Now, the next question is the next thing in my list is why string theory, right? Why string theory? So why we're interested in string theory? So I think the history can sort of answer some of it. So the string theory unifies GR and quantum mechanics, right? And it's a quantum theory of gravity. And as I mentioned, there is an argument that's probably the quantum theory of gravity. But again, there are lots of counter arguments there. So, but that's sort of the expectation. Now, another thing I think that became more of string theory in recent years is that string theory provides a new perspective on gauge theories, understanding gauge theories. So, when people say they do string theory in recent years, what they do is basically work in this particular direction, which is what you call the ADS-CFT. So string theory, from string theory, we have this conjecture called ADS-CFT, which gives us a completely different way of looking at gauge theories. So for example, there's this from this ADS-CFT duality, there is this notion called holographic entanglement entropy, which actually is a way to probe inside the interior of a black hole. So it relates all these cool areas of research. My recent research interest on holographic complexity is also sort of originated from this line. Now, another interesting thing about string theory is string theory provides new insight, new results in mathematics. So, roughly speaking, the relation between physics and math is sort of like an one-way direction. So it's like physics always took things from math. Now, with the string theory, it's actually somehow returning things to math. So string theory ideas suggest new direction insight for mathematics. For example, mirror symmetry, which talks about the relationship between topologically different Calabi-Yau manifolds. So there are a bunch of reasons why one should be interested in studying string theory. But of course, if I say all these good things, then the question is, is there anything wrong with string theory? Is there any problem with string theory? Now, so one of the problem with string theory is, so at the end of the day, we want to do physics, right? We want to connect our math to real world somehow. So in string theory, string theory talks about this extra dimension and other exotic ideas such as supersymmetry or user supersymmetry. But then the problem is there is no experimental evidence yet of any of this. And not only that, string theory cannot make unique predictions for low energy physics, fair to say. There is no convincing cosmology or particle physics yet, like fully convincing cosmology and particle physics. So, there are lots of models, but these models are completely flawed. So what I mean is, let's say I want to get an inflationary model of cosmology originating from string theory. Right? String theory is a fundamental theory, so it should give us this other theories. But it failed. And similarly, for particle physics models, right? There are lots of models, but there are lots of flaws and so on. And of course, earlier I mentioned that there are lots of extra junk and stuff that it's very difficult, extremely difficult to get rid of in string theory. That usually comes from extra dimensions and so on. So yes, so that's the problem. We couldn't connect. We haven't seen any experimental signature or experimental connection. Okay, so I think let's get to business now. With this background, I'm gonna start with the next topic. I'm gonna briefly talk about the units now. So if you have any questions, please feel free to ask. Okay, because with the Zoom talk, it's very difficult to know what people are thinking. Okay, so let's start with units. Now, I'm going to start with the Planck unit first. So what is the idea? So we have this three fundamental constants, like this Newton constant, which is 6.67 times 10 to the power minus 11 meter cube kilogram second square. There is speed of light, which is 3 times 10 to the 8 meter per second. And there is this Planck constant, which is 1.06 times 10 to the power minus 34 kilogram meter square per second. Something like that. Now, in Planck units, these fundamental constants are, we take the numerical value to be 1 in Planck units. So basically, we're looking for new units, which we call the Planck units. And in this unit, these fundamental constants take the numerical value 1. So what that means is I can write down G as 1, some length unit as here, some mass unit, which I'm calling the Planck unit now, and then time, Planck time squared. C is going to be 1 length and time. H bar is going to be 1 Planck mass, Planck length square, something like that. And and then from this we can get the Planck length to be, you can something like this, which is 1.61 times 10 to the power negative 33 centimeter. Right? So it's a very, very tiny length scale. Planck time can be written as this, which is h per c over to the power 5 square root. Right? From manipulating these expressions. And finally, the Planck mass can be h per c over g, which is 2.17 times 10 to the power minus 5 gram. Right? So it's a very, very, in kilogram minus 10 to the minus 8. Now, the Planck mass corresponds to an energy of, so this Planck mass corresponds to sorry, to an energy of, so, we use this Einstein relation. So it's going to be 2.176 times 10 to the 8 kilogram. And then this is the speed of light square. So it's roughly 1.955 times 10 to the power 9 joule. And then we can convert it in GeV. So in GeV unit, it's basically 1.22 times 10 to the power 19 GeV. Right? 1 GeV is like 1.6 times 10 to the power negative 10 joule or something. So this is the Planck units. But in our case, in string theory, we're going to use what we call the natural units. Right? So this is slightly different than this. So in string theory, we use this unit where we're going to set h bar and c to be 1 only. So in natural units. So, in this unit, the Newton constant can be written as sort of from here, m Planck square. And I'm using a slightly different notation here. This big M Planck is basically the reduced Planck mass. So it's like m Planck mass is the Planck mass over this factor 8 pi, something like that. Now, in this natural units, we get the, we can write this Newton constant to be, when I plug the reduced Planck mass value. So reduced Planck mass would be 2 times 10 to the power 18 GeV scale. And this is roughly 1 times 10 to the power 19 GeV, right? In the Newton, the inverse of the square root of the inverse of the Newton constant. Now, the other thing we have in this unit is mass, energy, and momentum. They have the same dimension. We call it the mass dimension. So, for example, you know, the speed of light is 1, so we can write down this dimension. So we can write down that L equals T. Right? So there, and then also from h bar, we can relate this to, so the unit for h bar is the dimension, so h bar is this. Now using this, we can get that this is basically, so all the units, length, time, can be related to the mass dimension. So everything can be written as a mass dimension. And so that's what happens in this metal. Okay, good. So that's the quick discussion about the units that you're going to see when you open a textbook in string theory. Now, I'll move to the relativistic strings, right? So basically the core of this lecture, the main part of this lecture. So let's move on to the relativistic strings. Okay. Okay, let's try. Oh, no, sorry. What did I do? Okay. Now, so what I'm going to do is when I talk about the relativistic string, because before talking about the relativistic string, I will start with the relativistic point particle. So let's start with relativistic point particle, right? To gain some insight, and then we will move to this string. So, so we're going to consider a point particle, a particle of mass m, and we're going to consider d-dimensional. It's in a d-dimensional Minkowski space time. So something like 1d minus 1, something like that. So the the metric we can write it as so Minkowski space time. So it's flat, so just plus plus 1, right? It's a d dimension. So this is d minus 1. Now, if we consider a coordinate frame with coordinates, so consider, oh, sorry, bad color. Consider a coordinate frame with coordinates x mu equals this time and space. Right? Then we can write the action. Then we can write down the action as this. Let's use a different color. dt 1 minus x dot x. Sorry. Now that's, you know, that's a well-known in GR. Now, the problem here is you can see that this is not covariant. Right? in the sense that this here t here t and x, they have different role. Time is a parameter in this case, so they look different, right? Here t and f are different. Now the question is, can we find an action or Lagrangian in which the space and time are on equal footing? So like enforcing Lorentz symmetry. So how can we do that? So of course, if we try to do that, then one way would be, I guess, to promote the time to actual degrees of freedom. Right? Not really a dynamical degree of freedom, but just promote it as a degree of freedom. Now, how do you do this? So let's consider. So let's promote t time. So promote time to a degrees of freedom. Now, how do you do? So then we consider the action. Consider the action. S equals minus m d tau minus x dot mu x dot nu eta mu nu. So what we have here is x naught is basically playing the role of time, and mu in the mu index is a space-time index, so it goes from 0 to t minus 1. And this x dot mu is basically x mu with respect to some tau. So to make it to have sort of equal footing for time and position, when you promote this time as a degrees of freedom, and then we consider this action, so it looks, there's Lorentz symmetry now, but the question is, we had to introduce this new parameter. So we introduced new parameter here, which is tau in this case. Now, the question is, what is tau doing, right? What is this tau? What is tau doing? So this tau is basically is labels the position. So it labels the position along the wall line of the particle. So if I do a cartoon, it's gonna look something like this. So I have this x naught, and then x the other directions, and then this tau is basically labels the position of this wall line, like this. So this action is just sort of like a proper time of the wall line, right? This new action. Now, what is our degrees of freedom here? So what is now the degrees of freedom? Now, so we have this now, right? So we have x naught is basically parameterized by this tau. Xi, the space coordinates are parameterized by tau, right? Something like this. Now, since x naught or t is now dynamical, so it looks like we have basically d degrees of freedom. So it looks like we have d degrees of freedom rather than d minus 1. Right? It looks like, because, you know, we promoted time. But this actually false. This is an illusion. Now, the reason is that this action that we wrote, it needs to be reparameterization invariant. So what do I mean by that? So notice that we, you know, here tau doesn't have any physical meaning, right? We can just consider any other tau, which is a function of this tau, some monotonic function. That will do. That will leave the action invariant. So we have this freedom of choosing a tau. So what that means is we call it. Let me write it down. So we call it that the action needs to be, or actually is reparameterization invariant. What I mean is I can choose another tau, which is a function of the starting tau, and we'll get the same action. So the upshot is not all the degrees of freedom are actually physical. So there, it looks like there are d degrees of freedom, but not all of them are physical degrees of freedom. Now let me quickly show that this actually works. So if we have this reparameterization, then the integration measure in the action is gonna look something like this. And then the action, sorry, bad color. And the action we can write as minus m d tau x dot mu eta mu nu. Now, just to be clear again, these are basically our space-time coordinates, right? Which is parameterized by tau now, right? So this is a space-time. So this is a space-time index, and it's parameterized by tau. So this should be the same as minus m d tau twiddle dx mu d tau twiddle dx nu d tau twiddle eta mu nu, right? Because that's what the reparameterization invariance means. The action is invariant. Now notice that if I start from here and then sorry, let's start from here and then replace it by the twiddle. So if I start from here and then replace it by the twiddle, so I replace this by the twiddle, tau d twiddle, and then this is gonna be minus dx mu d tau twiddle, but then d tau twiddle d tau, and then dx nu d tau twiddle, and then d tau twiddle dx, sorry, d tau, and then eta mu nu, and you can see immediately that this is going to give you that. So the upshot is because of this reparameterization invariance, not all degrees of freedom, all d degrees of freedom are independent. Now, by using this fact, by using this freedom, now we can set a gauge, right? We can set by using this freedom, now we can set tau, which is x naught, right? In our language, to t. Sorry, sorry, I said it the other way. We can set x naught to which is t to tau, right? In this. Now, or setting t equals tau, basically, that's what I mean. Now, if you plug this, now if you plug this to your action, then you'll get back the original action. Right? So, so this reparameterization invariance is basically some sort of gauge symmetry, right? So it basically implies a redundancy in our description, right? Because we can always switch from tau to tau tilde and so on. So what is the upshot here? So let me put it here. So we basically this reparameterization invariance is basically some sort of gauge symmetry, right? And if you look at carefully, so what happened is, so we made the action Poincare. We made the we enforce the Poincare symmetry in the action, and the cost we pay is this introducing a gauge symmetry, is a gauge redundancy in the system. So when you demand the Poincare invariance, we basically the cost we pay is the system has a gauge redundancy. So that's the point. So I can write down the action has Poincare symmetry at the cost of introducing gauge symmetry. Okay. Now let me show you a quick proof that there's a fake degrees of freedom, as mentioned earlier. So let's consider the conjugate momenta, right? So let's consider. So I'm now showing that there's fake degrees of freedom. One of the degrees of freedom is fake. So now consider the conjugate momenta of the particle. So we get P mu, which is right, that's the definition. So we get something like, when you compute it carefully, you'll get something like this. And then downstairs, you'll have minus x dot lambda, x dot rho, eta lambda rho, something like that. Now note that this momenta actually satisfies P mu plus m square equals 0. So it tells us the momenta are not all independent, right? Because we have it has to satisfy this condition. There's a constraint in the system, and this is called the mass shell constraint. Okay. Now I'm still talking about relativistic point particle, right? So I'm going to do one more thing before we move on to the string action. So in this point particle case, so we have this, right? So we have these functions which are basically some smooth map from the wall line to the spacetime manifold, right? The spacetime manifold. It's called space. And some smooth map. It's from we're mapping from some tau to the x coordinates. Now, when we have this kind of map, then we can think of in a differential geometry sense, you can think of an induced mapping. So what I mean is, if we define a space-time metric, right, some Minkowski or whatever space-time metric is, then you can find the pullback of this metric on the wall line. So if we have a, let's say, Minkowski metric on our space-time, which we started with, right, Minkowski space-time, then the pullback, I'm going to use this notation. So I'm calling this the function, the smooth function from the wall line to space-time. Right? So then we can have a pullback metric. And, you know, this is just a one-dimensional, it's like a curve, right? So wall line is just a curve. So it's a very simple one. So the pullback metric is going to be something like this. And then it's a metric, it's a tensor. So you have this. Now, notice that these components, the components of this tensor, this induced metric tensor. So what are the components? So let's say you set mu nu equals 0, then you get dt, d tau square eta 0, 0. So you get something like dt over d tau. And also, before that, you can already see that this is sort of the thing that we use for our action, right? We use this as the ingredient for our action. So you can already see another way of seeing the action here. Now, let's continue. So here we can also, the other components is going to be xi, d tau square, let's say ii. The rest will be 0, right? So it's going to be dxi, d tau, something like v square, right? So velocity square. So notice that this quantity, this gamma tau tau component of the tensor is basically dt d tau square 1 minus v square root. And for t equals tau, we get back 1 minus v square. Right? Something like that. So what I'm trying to say here is action can be seen as also the integral of the pullback metric. Now here we are, it's basically a one-dimensional case. So it's the pullback metric. It's the components, the square root of the component itself is a scalar, so it's fine. But when you have a like a 2 by 2 or higher dimensional metric, then it's going to be the depth of the determinant of the metric. Right? So that's. Now another point here is this is basically implies that this is proportional to the, because this is the induced, this is the square root of the induced metric. So this is basically the proportional to the length of the curve or the length of the wall line. Okay, so this is the action is proportional to the length of the wall line. Okay, now we are ready for our string actions. So a particle sweeps out a wall line in Minkowski spacetime. Are there any questions?
Yeah, could you say again what the pullback metric means physically?
Yeah, so so if you think about in the differential geometry sense, right? So what do we do in a differential geometry, right? So we have we have this. Sorry, what did I do? Oops. Okay, one sec. Let me fix this. Okay, yeah. So what we do is in differential geometry, we talk about smooth functions between manifolds. Okay? So this could be. This is a generic picture, right? So in our case, one of the manifold is basically just the wall line, and the other one is the spacetime. But it could be any general manifold, right? So this is a generic idea. So when you have a when you have a mapping, a smooth function between two different manifolds, then we can have what you call the induced mapping from this smooth function. The idea is the following. So if we define objects, let's say on this manifold, so by objects I mean like vectors, like tangent vectors or tensors or things like that, then by using this smooth function and its inverses, we can pull it back and find an equivalent function, equivalent object in the other manifold by using the function. And that's what we call the pullback metric when the object is a metric. Okay.
Right. But the word line is also embedded in the manifold, right? So isn't the metric already defined on the word line?
No. So you have a space-time metric, right? So you can think of a map, a smooth function. So these x's are a smooth function between your wall line and the space-time, right? So from that, your space-time metric can have an induced pullback metric on the wall line.
Okay.
And what we are seeing is action is secretly also some version of that pullback metric or square root and so on.
Thank you.
Okay, good. Now we have the basic ingredients. So let's move on. So the idea is, okay, we are talking about the point-like particles, right? Which sweeps out a wall line in Minkowski space. So therefore, if you think of a string, it's gonna sweep out the surface, right? A curved surface. We call it a wall sheet. So so let me call it, the name is Nambu Goto action. Okay. For the string. Right? So what we're doing here, so we saw that wall line and was basically some curve. And now we are talking about a surface when thinking of so again, the idea is in string theory, we are talking about instead of point-like particles, we have, closed strings. Right? There could be open strings. I'm not going into that mess today. Maybe when Tibro talks about d-branes and so on, he'll touch that. But the idea is very similar. The discussion is very similar. So we have this, closed objects, right? Closed loop-like objects. Now, so the corresponding the generalization of the wall line is what we call the wall sheet. Right? So here we needed one parameter. So of course, for this, we're gonna need two parameters. So we choose one time-like and one space-like coordinates for parameterizing the wall sheet. Okay. Now, we'll also consider, as I said, closed strings. So there will be some sort of periodicity condition. And the periodicity condition is going to be something like that this space-like coordinate is going to be period. So it's going to be like 0 to 2 pi or something. It's a periodic coordinate. So if I show it in a cartoon, it will look something like this. So we had this before, right? We have this wall line before. But now what we have is the following. Something like a wall sheet, right? And this is the tau, right? And this is sort of the sigma, right? These two parameters. And sometimes in the string theory language, we call the space-time as the target space, right? So the string sweeps out the surface in the target space, which is the space-time, which is this. So now we write down our coordinates as x mu. Now there are two parameterization, tau and sigma. And for the closed string context, this is tau sigma is equal to x mu sigma plus, okay, let's switch the order. Sigma comma tau, so it's 2 pi tau. right? Something like that. It's because of the periodicity. Now these are our string coordinates, right? Now, okay, so, and of course, as you have seen for the point particle case, we will also demand reparametrization, invariance, and so on, right? So there is no physical meaning for this tau and sigma, right? We can always reparametrize it. We can always find a new set of parameters. So from the previous single particle, point-like particle discussion, so now we kind of guess that the action of a string is going to be proportional to, it was the length of the wall line, right? It's proportional to. So, we can just extend the idea, which would mean that the area of the wall sheet is the, I'm using this for short for wall sheet, right? This is wall sheet. Now, so the question is, how do you find this area in terms of this x mu, in terms of this coordinates, right? So how to find it in terms of this x mu. So again, the idea is the wall sheet is a Kappa space embedded in the space-time, right? So you can think of an induced metric on that, which is again the pullback on the pullback of the flat Minkowski metric, right? On the wall sheet. So we know so I'm going to write down the pullback metric or the induced metric as gamma alpha beta. And I'm going to explain in a second the notation. So what I have here is, see, I have this space-time indices, right? These are the space-time index. But I also now added this another index, alpha beta. So these are what you call the wall sheet index. So alpha beta is, so A equals 1, maybe tau, A equals 2, maybe sigma, something like that. Right? So there are just two index, there are just two dimension. Now, so this is the induced metric on the wall sheet. Therefore, from the same, just generalizing the same logic we had, the action we can write down as this. Now we have integration over, so this is the shorthand for d sigma d tau, basically. Right? So this is shorthand for d sigma d tau, something like that. And we're gonna write it as the det of gamma, right? Just as the point particle case. Now, you see here I have introduced this new object, which is called the tension, which is basically some sort of proportionality constant. So this is tension, right? We demanded the action is proportional to the area, right? So there's a proportionality constant, and this is the tension. And we'll come back to this quantity a bit later. Right? So for now, just before that. So let's work this the components of this induced metric. So what are the components? So if I carefully compute them, it's going to look something like this. So here I didn't actually, so what is the, just explain the notation here. So here I didn't actually sort of suppress the space-time index, because when it's doing things from the wall sheet, can you see the full screen, or is it, maybe I just get rid of that. Okay.
Yes,
So,
we can see the full screen, yeah.
You can see the full screen, right? Okay. I was having some. Okay, so so here I basically suppress the space-time index. So for example, when I say this, what I mean is x dot is basically x mu d tau, right? So we're basically interested in things from the worldsheet perspective. So I'm just suppressing the space-time index here, just to make it just to avoid the index clutter. So and then x prime would be dx mu d sigma, right? Something like that. So so we can write down the action now as square root of, so let me put a line here. Yeah. So you can write down this as square root of minus x dot square, x prime square, plus x dot x prime square. I'll write the full thing in a second. Then you'll see what I mean. So let me write it more explicitly, because this might be a bit confusing. So what this means is, this is in full, like if I bring back all the indices, something like dx mu d tau minus square root dx mu d sigma square plus dx mu d tau dx mu d tau times dx nu d sigma dx nu d sigma. So as you can see, this is what I'm calling minus x dot x prime whole square, and this is what I'm calling x dot square x prime square. And so in this notation. Okay, now so we have the action. We write down the string action. The question is, what is the equation of motion now? So we write down the equation of motion as in this form, in this way. So x mu plus d sigma, similar thing, d sigma x mu plus
sorry, just to be clear really quickly, we just suppressed the eta mu nu, or is it actually not there? It's still there, right?
Yeah, it's contracted. Yeah, it's there, but
sorry.
just for avoiding the clutter, yes, we are not showing it. Yeah. So
Gotcha.
for this, that's why I wrote it here. So for this, I'm going to use this notation.
Sounds good. Thank you.
Okay. So this is these are the conjugate momentas, right? The conjugate momentas. So for example, this is tau mu, and this is going to be sigma mu, something like that, right? The two conjugate momentas. Now, so if I work it out, I'm not going to show the full. I'm not going to show the full details of the computation, but just I'm going to. It's your homework to figure out to do this computation in details. So you're going to see, you'll get something like this. Again, I'm going to suppress some indices just to make it look nicer. X prime and x u prime minus x prime square x dot mu, and then this ugly looking square root minus x dot square x prime square. So this is one of them, and the other one would be equally ugly. X prime, it's going to be something like x dot x prime x dot mu minus x dot square x prime mu divided by this same factor here. So, so you can imagine the equation of motion, how the equation of motion will look. I mean, here we don't have any direct coordinate dependence, right? So our equation of motion is going to be something like pi tau mu over tau plus pi sigma mu over sigma equals 0, something like that. So it's incredibly nasty and nonlinear equation, right? So it's not good, and so you get something very nasty. Now it turns out this is again this is a homework. I'll do when I do the Polyakov action, maybe I'll do it here, but here I'll just leave it for homework. One can show that by using the definition of the pullback metric and also this statement. This is when you do a variation of the determinant of the metric, we get something like this. You have seen this in GR. I'm not going to prove this. Something like this, right? You get that. So by using this and the definition of the pullback metric, it turns out we can get this equation of motion in a slightly nicer form. So it looks like we can put it back. We can put it in this form. Okay. Sorry. We can put it in this form, which is it looks a bit nicer, but it's still quite complicated, but at least nicer, right? So try this is try this. Try to get to there. I'll do it for the Polyakov action. I mean the next action. So like I'm going, I already going to mention it. So the problem with this Nambu-Goto action is this this nasty square root. So what happens is this make the whole quantization, especially the path integral quantization process, very different. So what we're going to do, we're going to use a different action, which is classically equivalent to the Nambu-Goto action, and which we call the Polyakov action. Right? That's going to be the next topic. Which is for quantization, which is much easier to deal with. Right? So that's the idea. Now, before going to the Polyakov action, let's talk about that thing that I didn't go over, that tension, this thing, right? This new quantity, this proportionality constant, tension, right? So let's spend a little bit of time on that. So I'm going to call it string tension and dimension. So what I'm trying to explore now, what is the physical interpretation of T, right? What does this T mean? Right? What the T means. So I'm going to work on the Minkowski coordinates. So I'm going to write down x mu as, let's say, T and x this. And I'll also work in a gauge, I'm going to make a choice for x naught, I mean, which is r tau. Now, this r here is just a constant that we need to fix the dimension. Right? But yeah, so there's nothing deeper here. Now, to get a sense of what this T is, what I'm going to consider is a snapshot of the string configuration at a time, right? Just a snapshot at the, so we're going to freeze the time, right? Just take a snapshot. And the demand I make is I take that snapshot when or snapshot at a time when the velocity or the momentum is 0. So that means at that point there is no instantaneous kinetic energy. Right? At that moment the kinetic energy vanishes. So instantaneous vanishes. Now, if I use this, so I'm not going to write all the terms, just to give you some, show some terms, just to give you the sense. So, our action has this form, right? This x dot square, x prime square, then x dot x prime square, something like that. So let's look at let's expand it a little bit and look at some of the terms. So you see, we get terms like dx naught, d tau. You can do it in exhaustively, but I just did it a few times just to get a sense. And then x mu tau with some extra pieces. Then there is terms like x naught d tau, dx naught d tau, dx mu d sigma, and then dx mu d sigma, and some other terms. So the point is, all of them actually will vanish because of this condition, right? Because you're taking a snapshot. So whenever you see mu, that means that's the basically, maybe mu is not the right index, right? So maybe I should just write it as vector, right, like this. So like lots of them, so all of them is going to go 0, and this is going to go 0 because this is time and this is space, and only this term, this kind of term, will survive, which means if we simplify, we're going to get something like this. I mean, there's nothing fancy here. You just have to carefully work out all the terms and just see how it goes. The sigma are the x d sigma square, something like that. So you see, this is quite nice because this means we can write down the action as dt, right? dt times this spatial length of string, right? Because this is ultimately, you observe that you get this dx, right? So this is basically corresponds to the spatial length of the string. Now notice that when this kinetic energy at that instant, when kinetic energy is 0, action is basically proportional to the integral of the potential energy, because there is no kinetic energy. So if I combine these ideas, what we get roughly is the potential energy is T times the spatial length of the string, which means T is basically potential energy over length. And we know that that's what you call tension. So that's the sort of the significance of that. Now, sometimes there's some historical reason. I'm not going into that. We don't have the time. Sometimes we write T as 1 over 2 pi alpha prime. Now, this quantity is called, as it looks like, alpha prime. And this is, there's another name, it's called the universal Ricci slope. Okay. So I'm just going to call it alpha prime. In our discussion, maybe you'll see a little bit of this again when Tibra is going to talk about other things, but in our lecture, we don't really need much of this. Now, one can see that the dimension of the tension is actually 2, which comes from the action, right? Because we want the space-time, this x dimension to be -1, and the sigma to be 0, right? Because it's not really a physical physical coordinate. As you can see that we use this periodicity condition, sigma plus 2 pi, right? So this is just a number. Therefore, if the tension has dimension 2, what that means is this alpha prime has dimension -2. What that means is, and it's the mass dimension, right? So it's -2 means I can relate a length scale with alpha. Alpha prime. How is that? So we can write down this alpha prime as some length, because it has 2 length dimension, right? Length square dimension. So this alpha prime we can write is some length scale squared. And this L sub s is called the string scale. Like the LP and Planck scale, right? And it turns out the string scale and Planck scale are roughly close. String scale is slightly smaller than, I guess, order of magnitude smaller than the Planck scale. But I think you might see some of this again when Tibro talks about ADS-CFT, right? So maybe you'll see that. Okay, but my discussion about this is here. I'm stopping. Now, before moving on to Polyakov action, let's talk about some symmetries of this Nambu-Goto action. Right. So, what are the symmetries of the Nambu-Goto action?
All right, Shajid. So before you move on, there's a question in the comments.
Yeah.
And
what is that?
Maybe if it is the right time to address that, well, I'll just convey it to you that can we generalize strings to sheets?
What do you mean, like considering an object?
Abdul Rahman, if you can elaborate it or maybe unmute yourself and what you're trying to ask.
So are you asking, instead of strings, can you think of like a sheet-like object as the fundamental blocks of nature? Is that what you're asking? So actually, there's this notion called actual strings versus fundamental strings, right?
Okay.
And so what I'm talking about, what you call this actual strings. And in a fundamental, so remember when I mentioned about the history, I mentioned that there is there is also some other stringy-like idea comes from the flux tubes in QCD, and in it also there is a similar notion in superconductivity, some sort of flux tube kind of thing, and those are basically this example of actual strings, and those actually do have some length scale. So on top of the tension, they have some length scale. But what we're considering is called the fundamental strings, and we're considering that length, the width of this string is actually 0. And when you do that, you can actually capture I can capture the action just by the Nambu-Goto action. But if you demand some width of the string, like an actual string, then you need to add extra terms in your Nambu-Goto action. We're not going into that. Now that's
so I think, if I understand correctly, he's probably asking about whether strings can be generalized to higher dimensional objects.
I see.
That's what the sheet is about.
I see. So, we are already making things way complicated, right? So you want to make things further complicated. So, I mean, we always look for the simplest thing. I don't know, maybe you can generalize it in principle, I guess, but what is the point? What is the purpose? Right? So if I can generalize all the theories just from string, we don't need a sheet, right? I answered it that way. Okay. I hope that answered your question. Okay. So the next is what are the symmetries of this Nambu-Goto action? So of course, the first symmetry is the Poincare symmetry of spacetime. right? So, we have this x mu goes to lambda mu nu, x nu plus something like that. So it's a Poincare symmetry. Now, from the Walsh perspective, it's actually global symmetry. So what I mean is these guys are constants from the Walsh perspective. They don't depend on the sigmas. Right? So this is a global symmetry from the Walsh perspective. Now, so that's one. And the second thing is we have reparametrization invariance. Right, which we have seen already that this sigma A can be, we can pick a different sigma. There is no special physical meaning for this sigma. And this is basically, as you have seen before, this is basically a gauge symmetry. So we have some redundancy in our description, since we can choose coordinate sigma as we wish, and it doesn't have any physical meaning. Okay, I think we're done with the Nambu-Goto. Now I'm going to move to the other action. I said is more useful in other aspects, in quantization and so on, which is the Polyakov action.
Okay, before that, there's another question that you
Yeah.
may read in the chat, but I'll also, speak it. The kinetic energy that we made zero and the tension only relates to potential energy. What does that signify? Are we
Right,
talking
so-
about stationary
yeah.
strings?
Yeah, no. So, okay, no. So you see, we are trying. So that was like a sketchy way of trying to understand what that T physically means. So since we are trying to understand what T physically means, we just created like a special case, and moreover, we're just looking at a snapshot of the string at a particular moment. It's just a convenient choice to understand what T means. That's all. We're not restricting the strings anyway. We're just looking at a particular moment of the string, just to understand what this quantity T means, right? To extract the physical meaning of the quantity. But we're not restricting the strings in any way. It's just a snapshot, not a generalized statement.
Okay, there's another question that if whether gravity enters string theory due to reparametrization.
Reparametrization is, I don't understand your questions. Gravity enters in the theory due to this. No, reparametrization is basically, as I said, there's some gauge freedom in your, there's some redundancy in your description. That's all it means.
I think, can I jump in and
Yeah,
contribute?
Sure.
I think
Yeah.
Yeah, you're right. Sajid, is reparametrization is the reparametrization of the worldsheet, right? So it's not the reparametrization invariant of space, time, and GR. So no, I think that's not the right way of looking at it. Gravity enters because the massless excitation of strings have a spin 2 particle.
Yeah. Okay, good. So are there more questions? Sorry. Oh, what happened? Oh, okay. Okay, cool. So so now we're gonna move to the next next section, the Polyakov action. So I'm gonna write down the Polyakov action and then explain explain afterwards. So the Polyakov action goes like this. So this action is basically what we have done here is we have introduced this dynamical metric rather than this in the Nambu-Goto action. You have this Walsh-Schmidt induced metric, right? So we have a dynamical metric here of the Walsh-Schmidt, and this is from the index. You can see that this is basically a metric on the Walsh-Schmidt, right? So we have, instead of when you think of a metric, right? I mean, in principle, I mean, we have been using space-time metric, but this is not a space-time metric. It is the Walsh-Schmidt metric. It's a metric on the Walsh-Schmidt. And the action is basically, from the Walsh-Schmidt perspective, it implies it's an action that is where there's a scalar field which is coupled to a two-dimensional gravity, right? Because there's this 2D metric introduced here, like a Walsh-Schmidt metric introduced here. Now, the reason, I mean, we'll see how these two actions are equivalent in a second. So you know, to show the equivalence, I'm gonna quickly show the equation of motion. So again, if I use the Lagrangian as I'm going back, I'm switching between alpha and t, so I hope that's not a problem. Alpha beta, alpha x mu, beta x nu. And then I use the Euler-Lagrange equation. So this is 0. So what I get is, from here, what I get is this guy is basically equal to and here we have something like that. And then this is equal to x mu. So you can see finally the equation of motion becomes something like this. Now notice that this is very similar to the equation of motion we got from the Nambu-Goto action, right? We had this this action there, which I didn't prove. But you know, when you put things in a slightly nicer form, we get that action. But there's a difference here. These guys are independent variables. So they have their own equation of motion, and we have to find this equation of motion, so which is not different. So to find this equation of motion, we're going to vary the action, right, with respect to the metric. So we are going to use this variation rule I mentioned earlier. G alpha beta, G alpha beta. This variation rule, and then we can write down the variation of the action as the following. So we're going to get two terms. x mu, beta x nu, and then there'll be the second term, which is this. Something like that, right? Sorry, something like that. Now, to get the equation of motion of the metric, we're going to take the variation to 0 for any variation of the metric, which means we get this to be 0, which gives us G alpha beta equals something like this kind of form, where this F inverse is basically rho sigma x, right? I mean, from here you can immediately show this. Setting this to 0, you can immediately show that. Now the upshot here is what you're getting is this metric is not same as the pullback metric that we had in the Nambu-Goto action. So not same as gamma. And the difference is obvious. You can see that there's this extra function here, f. Now, at the level of the equation of motion, it's not a problem because, in the equation of motion, we have this guy and we have this guy. What is going on? And this guy, in this guy, the its scale is f, and this guy's scale is minus f inverse. So therefore, they basically cancel each other. So the equation of motion of Nambu-Goto is the same as the equation of motion in Polyakov. Now, now there's another interesting quantity that I will mention here, which comes from also from the variation of the action. So which we call the stress energy tensor. I think Tibro will need that later on when he talks about other things, ADS-CFT and conformal symmetry and so on. So this is the stress energy tensor is defined as with some numerical with some factors. This is basically the variation of the action with respect to the variation of the metric, some sort of functional derivative. Therefore, from here, we see that this is basically this quantity over here is basically the stress energy tensor. So what we get from the variation, because we already have the variation right here in the box. So when you write down the stress energy tensor explicitly, we get something like this from that expression. Now, notice that when you enforce the equation of motion for the metric, right, the dynamical metric G alpha beta, then this is gonna go 0. Right? That's how we got the metric in the first place. So this is basically what you call a constraint equation for our system. I'll come back to this again later. Now, let's talk about the symmetries of the Polyakov action, okay? Just like we did for the Nambu-Goto action. Okay. So we still have those two symmetries that we talked about in Nambu-Goto action, the Poincare symmetry This is again a global symmetry from the perspective of the wall sheet, and we also have the reparameterization. I'm actually already over time, right?
Yeah, like it's up to you if you want to
I actually wanted to
up or
go up to I had quite a bit actually, like the mode expansion, because if I don't do mode expansion, then I think Tibra is in trouble.
yeah, because the
So-
lecture is going very well, and I think all of us are enjoying. So that's why I didn't interrupt you.
Okay, so if you can give me a few more minutes and let's see how it goes, right? How far I
Yeah,
can go,
my
then
pleasure.
maybe I can try to cover in the next section. So we do have these symmetries, right? As the Nambu-Goto, as we've seen in the Nambu-Goto action. So we still we have these symmetries here also in the polyconvection, but the thing is here we on top of this we have another a new symmetry. We have a new symmetry, which is novel to the polyconvection that we've been seeing in the Nambu-Goto, which is this Weyl transformation. So what does that mean? So basically what that means is we can sort of change we can do a local change of scale. That means this metric, if we change it by some factor, tau sigma, something like this. We're not messing up with the x mu, right? Something like this. So this is, so we just rescale the metric basically. And this is a new symmetry that we haven't seen in the Nambu-Goto action. And this, as you have seen, scale as E phi this, whereas this scale as minus phi G alpha beta. So here I'm just using a slightly different notation, right? In the earlier I kind of hinted this by this function f, right? Here it's in a slightly different one. Sometimes you'll see that this is written in this form. Alpha beta is omega square, right? That's another way of showing it. There's different ways of writing that factor. Okay, good. So we have this X symmetry, right? So now we have lots of redundancy in our system. We're going to fix a gauge, right? We're going to fix a gauge. So let's do that. So fixing a gauge. Okay. So first redundancy we have is two reparameterizations, right? So for example, we had tau sigma. Now we can go to tau prime, sigma prime and tau prime, right? So there are two reparameterization you can do. Notice that this alpha beta, this wall sheet metric, it has basically three independent components, right? The diagonals and then the off diagonal element. There are three independent components. Now by using and we have this two reparameterization invariance. We can do two reparameterizations, right? So basically, by using this two of these reparameterization invariants, we can fix two of these degrees of freedom, two of these components. So by using the reparameterization invariants, we can fix two of those and write down the metric in this form. So this is here in this notation. This is basically the flat metric, like in a 2D conform, a 2D flat metric, right? 2D Minkowski metric, and this particular form is we call it this is a locally flat metric. Locally flat, sorry, locally conformally flat. flat metric. So you can write it like that. But notice that in Polyakov, we have an extra symmetry, right? This Weyl scaling, this Weyl transformation. So that's also a gauge symmetry. That's an additional redundancy, right? So you can use that third one to fix this guy as well and just make this completely flat by making use of these redundancies. So although we have a dynamical, like non-flat metric, by using these symmetries, we can actually make it a flat metric, like a flat Minkowski metric in 2 by 2, right? It's a two-dimensional shape. Okay, good. Now, how does this help us? Okay, let's go into that. So, of course, this will change our equation of motion, right? It will give us simplify our equation of motion. So remember that our equation of motion was this. Right? This was our equation of motion. Now, if we replace this this metric now by a flat metric, right, which means this is going to be now 1, right, and we can write down this equation, this equation simply as this is going to be just a flat metric, so you can take it out. So what you're going to get is alpha beta d alpha d beta x mu, which means d alpha d alpha x mu equals 0. And I don't know if you guys realize this. This is fantastic, right? Because this is our wave equation, favorite wave equation. So by using this reparametrization invariances and the Weyl invariance, we can actually simplify this to a wave equation. But there is a catch though. Remember that we had a bunch of constraints. We have a constraint because the stress tensor vanishes, right? That was our constraint. So let's look at the constraint now. So our T alpha beta was d x mu d beta x mu minus 1/2 g alpha beta g rho sigma rho x mu sigma x mu equals 0. That was our constant. Now, notice that with this new substitution, right? With this substituting this by the flat metric, I'm because of the time constant, I'm just keeping a few lines here. So by using the flat metric for the g mu for the g alpha beta, we can write it as d alpha x d beta x. I'm suppressing again the spacetime indices. Alpha beta rho sigma d rho x d sigma x equals 0. And more precisely, let's look at there are like 4 terms, right? So let's look at 0, 1 term. This is going to be 0x 0, 1x minus 1/2 eta 0, 1 equals 0. Now, since I know that the metric is flat, so this is 0, so I'm not writing down the rest of the things. So you can immediately see that what you get is x dot x prime equals 0. So that's our first constraint, explicitly written in terms of the coordinates. Similarly, you can show that the 0, 0 and the 1, 1 will give you this. They're the same, and they're going to give you this constraint equals 0. So what is the upshot? So the upshot here so far is, so we have now this equation of motion. So finally, we have this equation of motion, which is d alpha x, which is again again, the wave equation. And then we have constraints, which are T01 equals x dot x prime equals 0, and T00 and T11 is equal to 1/2 x dot square x prime square equals 0. Now, remember that we actually have one more thing on top of this, which is this periodicity condition, which you're going to also make use of. Right? This is also, we also have. So this is the periodicity condition. Okay, so now we're going to solve this equation. Of course, this is a wave equation. We know sort of how to deal with this. So the rest of the talk, can I get maybe another 15 minutes? Then I'll.
Yes, why not? Why not?
Okay. Okay, I don't want to bore you guys. But it's sort of like not the right place. I feel like not the right place to stop, right? So just give me a little bit more, time. And so now what we're going to do, we're going to introduce, to solve this, we're going to introduce the light cone wall sheet. So in the second lecture, I'll basically use the light cone quantization. So, that's one of the motivation for using this particular wall sheet, this particular light cone wall sheet coordinates. So I'm going to now change coordinates. So what do I mean by that? So now I'm going to solve this system, I'm going to introduce light cone coordinates. Of course, light cone wall sheet coordinates, right? Coordinates. So what that means is I'm going to call sigma plus as tau plus sigma, and sigma minus as tau minus sigma. Right? So instead of tau and sigma, I'm going to use sigma plus and sigma minus, right? Two coordinates. And these are, we call the light cone coordinates because, the associated coordinate axes are the wall lines of the light emitted from the origin along the sigma, right? So that's I think probably you're familiar with this. Now, in these new coordinates, so what are the derivatives? So the derivatives are going to be something like the tau plus minus d sigma. And we can write down the metric as 0, 1, 1, 0. Now, I actually wanted to show it explicitly, but since we're running out of time, so try this. This is a homework. Okay. Convinced that this is the metric. Okay, so now we're going to use this. So since we changed the coordinates, of course, we have to rewrite the things in terms of these new coordinates, right? So we have this equation of motion and its constraints. So let me write down the equation of motion and the constraints. So so in this new in light cone coordinates, what you get is the equation of motion. Equation of motion will become something like this. I'm going to show you it in a second. And the constraints is going to look like t plus plus equals x mu, x mu equals 0, and t minus minus is going to be minus x mu, and x mu is going to be 0, and these are just 0. Okay. Now, maybe very quickly, like not the full solution, but I can like a sketch how to get there. So remember that we have this equation of motion, right? So which means in terms of tau sigma, something like this. Right? In terms of in the original tau sigma notation. Now we have when you're using this, and then we can write down these derivatives as like plus something like that. And then we can write down d tau square in terms of these guys, and d sigma square in terms of these guys. And then when you plug it back to your equation of motion, you'll see that this expression immediately will come out. So plug this to equation of motion, then you're going to get something like this equation of motion. Right? So by following these steps, I'm just, due to time constraint, I'm not showing all the steps. Right? But the point is, it's just a coordinate transformation, right? You can do it. Now, similarly, for the constraint, first you write down this d tau tau explicitly in terms of x and like, for example, maybe 1 I can write. So something like this, right? D tau x mu square plus d sigma x mu square equals 0, right? And then you have d sigma tau, you have similarly sigma sigma, and then you can write down this t plus plus as you do a coordinate transformation, right? Like as a transformation properties of the tensor, sigma plus, this sigma b, sigma plus, and then t alpha beta, right? Something like that. And then you you expand it, and then you can show that you expand it, this TAB, and then you can show that this is basically d plus x mu, d plus x mu equals 0. It's going to give you this. So these are, very quickly how I get how we can get to rewrite this equation in terms of the light cone coordinates. So the upshot is, in light cone coordinates, this is our equation of motion, and this is our constant equation, right? So this is this option. Now, so let's get to the solution now. So our equation of motion is this guy, right? Now, the solution, a generic solution of this form, is something like right. I mean, this is basically a wave equation, right? So we know as a sort of how the solution of a wave equation looks like, right? Something like that. And we call them the right movers and right moving waves, and the left moving. Right? So this is that. Now the question is, what are the forms? I mean, these are arbitrary functions, right? So we need the form of this arbitrary function. Now, so how do I get this form of this function? So we're going to impose a bunch of things. So first, we're going to impose that. One of the things that we're going to impose is that we want these coordinates to be real, right? So x mu is, and it's equal to the conjugate of complex conjugate of x mu. So that's the real condition. And then we're going to use this this constraint, the constraint equations, this constraint equation, which can be written as I'll show you in a second. Constraints can be written as xr square equals 0 equals plus xl equals 0. And finally, we'll also, on top of this, we're going to also use the periodicity condition that I mentioned earlier. So we're going to use this to get a generic solution, right, of the equation, and basically get the form of this XL and XR. Now, I'm going to quickly show you how to think about this, not in details, but sketch it. So this is our constant equation. Right? This is our constant equation. So notice that I can write it down as XL plus XR. There is mu. I'm dropping the mu's. Okay, dropping the space-time indices. Dropping mu's for for avoiding clutter. And then there is and then the same here, right? The same for this guy. D plus, sorry. D plus, right? Same for the other XL, XL plus XL. Now, so if I expand this, what I get is this XL square. There's other terms like this, square plus dxxl, dxxr, and so on. Right? Now notice that this guy is 0, right? Because this is function of sigma minus, and this is also 0 for the same reason. Therefore, what you get from this is this condition, and that's what I wrote here. So our constant will essentially become like this. Okay? I just showed you the one of them. In a similar way, you can find the other one. Now, let's look at the periodicity condition. So I think when I was preparing this lecture, I was a bit sloppy. So I'm going to go back to the original coordinate just to make the point. Okay, but you can do it the other way. So let's talk about the periodicity a bit. So what we have is this, right? We have 0 tau, let's say. We have some x mu, 2 pi. Oops, what happened? Oh, sorry. What did I do? Okay. I got scared. Okay, good. Okay, good. So, no, what happened to the?
Oh, we
Oh
lost.
shit. Oh my goodness. Somehow I'm very technologically challenged. So I think I pressed something
It's
and
strange that it saved till the Polyakov action, but it didn't
it
save.
probably likes the Polyakov action. Okay, I'm sorry guys. So I'm gonna just jump to the discussion I was having. So I was arguing how to think about the periodicity condition. So we have x mu 0 tau, which is x mu 2 pi tau, something like this. Now, any field that satisfies this kind of condition can be expanded in terms of the Fourier expansion. So I can write down this sigma tau as like n minus infinity to infinity e to the power I n sigma f mu, f n mu tau, something like that. And notice that, so this is sort of our answers, right? Now our equation is basically the equation of motion, something like this. X mu sigma tau, right? Now if I plug this into this equation of motion, if we plug this here, so then what do I get? So I get plug 1 in 2. So I get something like d tau square fn sorry, mu tau equals minus n square Fn mu tau, right? Something like that. And it's nice because we know the solution of this kind of equation is Fn mu tau is going to look like some alpha n mu I n tau, and then beta n mu to the power minus I n tau, right? That's from differential equation, and n not equal 0. And for F naught, which is going to be basically a linear function of tau, some linear function of tau, right? These are a bunch of constants for now. So you can see, and of course it's a linear function of tau because then you can immediately see that if I do d tau square, F naught mu tau is going to satisfy, right? It's going to satisfy the condition. It's a quick check. So we get that the zeroth order term is something like linear in tau. It's cannot be linear in sigma, right? That is going to ruin the periodicity. So it's just a linear in tau, and the generic nth functions are these expansions, right, in terms of this. So what is the upshot here? So the upshot here is I'm just giving you the motivation for the generic solution. So the generic solution of our differential of our equation for equation of motion can be now written in this following way. So XL. So remember we had these two terms, the left movers and the right movers, right? So I'm going to write two different expressions. So for the left mover, we write x mu plus 1/2 alpha prime p mu sigma plus I alpha prime over 2, and then 1 over n not equals 0, alpha mu and I n sigma plus. So you can see that this is the 0th part, right? And then this is the more expansion. And for the right movers, we have...
what is P again? The P mu momentum?
Yeah. So I'll explain it in a second. But it's coming from this.
I see.
We just wrote a linear expression for the F naught. But there's a physical meaning. We'll get to that.
Okay.
Now x mu plus 1/2 alpha prime p mu sigma minus, and then I alpha prime over 2 n not equals 0, 1 over n alpha mu n e to the power minus I n sigma minus. So get this two different solutions. Now the physical meaning, and so this is basically, so you see when I add these two to get the x mu, I'm going to get an x mu. That's how these constants are set, right? So x mu is basically the position of the center of mass of the string. So this x mu implies when there is sort of no oscillation, right? Just the center of mass. Position of the center of mass. And this guy p mu is the total string momentum, which is sort of describing the free motion of the string center of mass. So this is momentum, and that's the reason for choosing these particular symbols. Now, one other thing that we kind of ignored here, we demanded that x mu is real, right? We wanted a real solution. So when you demand the real solution, that ensures that this x mu, so the reality condition, real x mu, would imply that this x mu and p mu are real. On top of that, it also will give us this other condition. You can actually show this. So the way to show this is you add the left hand side and the right, the left mover, the right movers, and then apply the reality condition that x equals x star. And then you might have to do some redefining of indexes and so on. So you can show that alpha mu n star, and you'll get alpha twiddle mu minus n is going to be alpha twiddle n star, right? So you get on top of the, you get a condition on the, also on the modes. Okay, almost there, almost there. Okay, 5 minutes. Sorry. So now we have this these two equations, right? These two expressions for XL and XR. Now let's call it equation star. Now notice that if I do this, which is basically if I break down this as a left mover and the right mover, so basically the left mover vanishes and the right mover survives. So you get that. So you can write it like this. And then if I operate that in this equation, you can see the R here, XR, right, the right movers in this star equation. Then what I get from there is, first is a constant, so alpha prime over 2 p mu, and then alpha prime over 2 square root, and then sum alpha n mu to the power I n sigma, and this is n not equal to 0. Now notice that if I define this guy, so for example, if I define this 0th mode, this p mu as this, right? So if I do that, then I can write it in a compact way, which is alpha prime over 2 square root. Now I don't have n0. I don't have to exclude n equals 0, right? I can include that n equals 0 in this sum. In the same way, sorry, one thing let's go back here, which I think I erased. So remember that our constraint equation essentially became this, right? This was our constraint equation. So when you do this, so this quantity boils down to that. So when I square that, what I'm gonna get is the square of that. So I can write it like this: MP, I need 2 index now, alpha m, alpha p, and then e to the power I m plus p sigma minus. And our constant tells us this is 0. Right? That was our constant. So notice that this I can write it as alpha prime over 2 sum, maybe just change it to n because we like n, right? So what I did here is I called this guy to be n, just renamed it, and then I can write it like that. And this you can package as sorry, I'm gonna observe alpha 2, the factor of 2. So you can package it as n ln e to the power I n sigma equals 0. So obviously here we're calling L sub n as 1/2 sum m alpha n minus n. Right? That's the L sub n. And these are called the Virasoro generators. You'll see that probably when, I don't know if they will probably talk about CFT a bit, so you'll see that there. Now, remember that we have the left movers and the right movers, right? So if we do a similar computation for the right movers, so we're going to end up with something like this. For the right movers, the other one. And then we will get a very similar condition for the 0th order. It's exactly the same computation, except we put a twiddle now. Okay? Something like that. So
you're promising a lot of stuff from me, Sajid. I'm getting scared.
Okay, so what we get here is we get is this alpha, this is equal to alpha naught mu, right? Because of course, because this is, as you can see, they are both identified with the momentum. And we get an infinite amount of constraints. So we get ln, because all this has to be 0, right? So that means ln has to be 0. So you get ln and ln twiddle, there has to be 0, where n is basically element of the set of integers. So you get this constant written in this way. And L naught, the 0th order, L naught is going to look like 1/2, if I use this definition of L naught and ln, it's going to look like alpha 0 minus m, alpha m, which means L naught can be written as 1/2 alpha minus m, alpha m, right? And then I can split the 0th order term, which is 1/2 alpha naught square, and then 1/2 alpha n, alpha minus n, where I don't have the 0 anymore. Now, notice that this is what? Again, I go back to the p. So this is basically alpha prime over 2, p mu, and p mu, right? Because p is related to alpha naught, plus the rest, alpha n, alpha minus n, and n not equals 0, something like that. Now notice that from relativity, we know that this must be equal to the mass squared, right? Because p mu this is the rest mass of the particle. Right? And in our case, this is basically the effective mass of the string. So, and I forgot the factor. So I have an alpha prime over 4 here. And then we get this 1/2 alpha n, alpha minus n, and not equals 0. Okay, so what is all this means then? So L naught equals 0, then mean, so you can see L naught equals, if I plug L naught equals 0, then what I get is this effective mass in terms of these modes, right? These oscillation modes. And similarly, of course, I'll get one expression. Similarly, I'll also get for the twiddle case, which I didn't explicitly do, but it's exactly the same computation. Right? So, so these are basically expression for the invariant mass in terms of the left and right movers, and it's the invariant, it's the same mass, right? So the point is they should be equal. As I did here. And there's a name for this. It's called level matching. So what this L naught and L naught twiddle are telling us is basically the effective mass of the string can be written in terms of the excited oscillation modes, right? Because you can see that these are basically the excited oscillation modes. Right? Okay, so I think I'm going to stop here, and next in the second lecture I'll try to quantize this system.
All right, perfect. And thanks once again. You spent, more than your quiet time. And I'm also grateful to Tibra for, staying all along and answering the questions. So, all right. So I'm stopping.